welcome to the Geomastic channel. In the last few lessons, we've gone in depth on different methods of finding missing angles and side lengths in right triangles. Today's lesson is going to put all these concepts together to undergo the task of what is called solving a right triangle, which simply means just to find the measure of every angle and the length of every side. If you'd like to follow along with me, you can go down to the link in the description to print off a guided notes worksheet that will follow right along with this video. You can write some things down and follow along. Now, since we're talking triangles here, there are going to be 6 pieces of information that we're going to be looking for to solve a right triangle. The 6 total parts, we've got 3 sides, we've got 3 angles. Now the good news is that we'll never have to truly find all 6 pieces because being a right triangle, we automatically have that first angle. We got that 90-degree angle cutting us down to 5 total parts. And we must be given at least 2 other bits of information to be able to use the techniques that we're going to apply today, which really knocks down our total of missing pieces to 3. Now, there's lots of different methods here that we can use to solve a right triangle. The first thing I'm going to do is I'm going to spend just a little bit of time on some special cases. I'm not going to spend a ton of time here just because we've already covered this in depth in a previous lesson, which you can find right up there. But I do want to touch on these just real quick. So the 2 triangles that we're going to look at first is what we call the isosceles right triangle. Isosceles meaning 2 sides the same. And I want to look at half of an equilateral right triangle. So equilateral meaning all the sides are the same. So half of that would kind of look like this right here. Okay, so these 2 special cases we're going to touch on real quick. Now, an isosceles right triangle, meaning again 2 sides are the same. This is also known as the 45-45-90 right triangle. And in a 45-45-90 right triangle, where 2 sides are the same, that also makes the 2 base angles the same, thus the angles being 45, 45, and 90. So if I'm trying to solve one of these, I've really already got the angles figured out. 45, 45, 90 are the angles. And let's say that we have a missing side here, a missing side here, but maybe we knew one of the sides down here. Let's say it's 6. Okay, so really we're down to 2 pieces of information that we're looking for to be able to solve this thing. If you remember your 45, 45, 90 rules, it shouldn't take too long because we do know, first rule is that the legs are congruent to one another. It's isosceles, I've got them marked. If this leg is 6, obviously this leg is also going to be 6. And then the last piece of the puzzle here is this hypotenuse, so this side y, this longest side. So the rule for a 45, 45, 90 is that the hypotenuse is equal to the leg times the square root of 2. Okay, in any 45, 45, 90 right triangle, whatever that leg length is, all I have to do is multiply that by the square root of 2, and that will tell me the length of the hypotenuse. So really not much calculation here. It's just you take the leg, 6, you multiply it by the square root of 2. You can get a decimal if you want to type it into your calculator, but an exact answer in this case, we're going to leave it as 6 times the square root of 2, and that's it. So we've got all 3 sides, we've got all 3 angles, we have solved that right triangle, 45, 45, 90. With this rule, hypotenuse is equal to the leg times the square root of 2. It's really all you need. Okay, so for the second one, half of an equilateral triangle. Now an equilateral triangle, you know it's all the sides are the same, all the angles are the same. So if I drop that altitude right down the middle, okay, perpendicular to that base, since I have cut it in half, a couple things that we know. Number 1 is that if all the angles are the same, 180 divided by 3 is 60. So I got all these angles are 60. Since I've cut that top angle in half, half of 60 is going to be 30. So that's why we call this again the 30, 60, 90. Okay, I'm going to get rid of this other half of the equilateral triangle. So we're just dealing with this piece. Okay, so we've got some special rules for this guy as well. I'm going to give you one of the lengths of the sides, and let's say the other 2, once again, are missing. Okay, so since it's 30, 60, 90, we've already got all 3 angles. We're just missing 2 of the side lengths. So your rules for this one, if you don't remember, Again, you can check that video right over there to give you the basics here, but what we're looking at is to find the hypotenuse. All we have to do is take that short leg and double it. So the hypotenuse is equal to the short leg times 2. And again, that's because if the whole side of that equilateral triangle is known, that short leg here is just half of it. So if I go ahead and double that, that's going to get us the length of y, which is 10 times 2, that's 20. Okay, so the hypotenuse is just the short leg, 10 times 2. And then finally, to get to the longer leg, which I'll abbreviate as LL, longer leg is equal to the short leg times the square root of 3. That's the rule that we found for that one. So if the short leg is 10, the longer leg, x, is just that leg, 10, times the square root of 3, which again, you can get a decimal if you want, but we're going to leave it as an exact answer of 10 root 3. And that solves the 30, 60, 90. When your triangles don't have these special rules, if you don't have an isosceles right triangle or a 30, 60, 90 right triangle, you can get a little creative with how you solve these right triangles. Now you got a couple of options that can both get the job done depending on what you have. But the main player here is to utilize your basic trigonometric functions of sine, cosine, and tangent. Now if that doesn't ring a bell, you need to stop here, head over to this lesson first, or else none of this is going to make any sense. Now, if you are familiar with sine, cosine, and tangent, you've likely used or at least heard of the mnemonic SOHCAHTOA. And this mnemonic helps us remember the ratios for each trig function. So again, that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite leg over adjacent leg. All right, so let's solve some right triangles. So our first one here, again, you always got a right angle, so that's 5 parts that we'll have to find. You're always going to be given at least 2 pieces of information. So let's say this is a hypotenuse of 14, and we'll call this a 32-degree angle. So here we're missing that angle up top, this side length, and this side length. So we got x, y, and z. So to find these 3 pieces, easiest of which is going to be this third angle here, since we've already got a 90 and a 32. To figure out that third angle, since a triangle adds up to 180, I can just subtract these 2 angles from 180 to get that missing angle. So starting with x, if I take 90 and 32, subtract those from 180, what I'm going to be left with is a 58-degree angle. So angle x up there, 58 degrees. Okay, so we've got all 3 angles. Now we're just down to 2 sides. What we're going to do is we're going to utilize our trig ratios here to figure out the lengths of these 2. So I'm just going to go about it one at a time. Since I've already got the hypotenuse, I can use both sine and cosine to get my missing sides. I just got to pick which one I want to go first. Let's go with y first. So it's always helpful, again, if you label your sides as opposite, adjacent, and hypotenuse. That's in relation to your acute angle that you're going to use. So if this is my 32-degree angle that I'm going to use here, opposite of that angle, the opposite leg is going to be here. So this is my opposite leg, so I'll put an O. My adjacent leg to the 32-degree angle is z, so I'll put an A for adjacent. And my hypotenuse here is 14. So if I'm going to solve for, let's go with y first. I know that y is the leg opposite of 32. I already have the hypotenuse here, 14. So the ratio that relates the opposite leg to the hypotenuse, O and H, I go up here to my mnemonic, O and H is right there. So I know that this is going to be a sine ratio to solve for y. So the way that looks is I take the sine ratio of my 32-degree angle. I'm going to make a ratio of the opposite leg over the hypotenuse, so that is y over 14. And then I put sine of 32 over 1 to complete a proportion. Okay, so I've got my proportion. To solve a proportion, we're going to take the cross product, or cross multiply 1 times y, which is y, and then 14 times sine 32. Okay, at this point, this is where I go to my calculator. So I'll move this up here. Make sure I'm on. Okay, go to my calculator, and I'm going to type in 14 times sine 32. 14 times sine 32. Okay, when I type in 14 times sine 32, that's going to tell me the length of that leg y, and it looks like we'll round to the hundredths place. It's going to be about 7.42. Okay, 7.42. Just to kind of check the reasonableness of my answer, since my hypotenuse is 14, I know my short leg is going to be less than that. About half the size of the hypotenuse should make sense, so that looks good. So y equals 7.42. Now I have a couple of options here to go about finding z, one of which is just to do another trigonometric function. I can use one of those, in this case it'd be cosine, to find z, that's what I'm going to do in a second. I could also use Pythagorean Theorem, since I already have two of the three sides now of this right triangle. I've got one leg is 7.42, the other side, hypotenuse in this case, is 14. I can use Pythagorean Theorem to find z, but I'm not going to do that here. I'm going to use another trig function. And I'll tell you why in a second. So the other trig function I can use in this case to find the adjacent leg z, I can use cosine. Adjacent over hypotenuse, right here, adjacent over hypotenuse a and h, we can use cosine. So same setup, it's just cosine instead of sine. Of my 32-degree angle, cosine is adjacent over hypotenuse, so that is z over 14. Okay, cross multiply the same way. I've got z times 1, which is z. 14 times cosine 32 is what I'm going to type into my calculator. So I've got 14 times cosine 32. And looks like we got about 11.87. So we've got z 11.87. So that solves this right triangle. All three sides, all three angles. 11.87 makes sense for this longer leg. It's longer than the short leg. It's less than the hypotenuse, so we know we're in the ballpark. All right, let's do another one. So our second example, let's go with this information. So in this case we've got two sides. Let's say neither of the acute angles are known, so x and y are going to be those two angles, and then z is going to be the length of the hypotenuse. Okay, so we've got, again, three things missing, two angles, one hypotenuse. We've got the right angle, 10 and 6 for the two legs. Okay, so in this case, we can't go straight to just regular sine and cosine or tangent functions because we're missing the two acute angles without any quick way to get those. So I'm going to start with z actually in this case because I've got two of the three sides of this right triangle. In the last example, I said we could use Pythagorean Theorem, but I'm not. In this case, I think this is going to be the quickest way to go about finding z. So Pythagorean Theorem, which is just, again, a squared plus b squared equals c squared, where a and b are your two legs, c is your hypotenuse. This is going to be the quickest way, I think, to go about here. So a and b, doesn't matter which one is which. We'll say 6 squared for a squared, 10 squared for b squared, and then c, which is unknown, c squared, z squared. Okay, so we go through. 6 squared is 36, 10 squared is 100. Add those together, 36 plus 100 is 136. And then last step here is we're going to take the square root of both sides. Square root of both sides here, that takes care of the square and the square root, so I've got z equals the square root of 136. Okay, z is the square root of 136. Now, I can leave it like this, maybe. Hopefully you can see that. Z is the square root of 136. I could type that into my calculator. So if I took the square root of 136, I could type that in and get a decimal, which looks like we're about 11.66. So I can say, we'll go over here, we'll say z is 11.66. I could simplify my radical. The square root of 136, I'll actually simplify down to square root 34. So if you're trying to get an exact answer, you can simplify that down. If you don't remember how to simplify radicals, you can find that video right up there. But in this case, we're just going to leave it as the decimal. I think that's fine for this one. Okay, so z, 11.66. I look at my picture, longer leg is 10, hypotenuse has to be longer, 11.66, a little bit longer, that looks good. Okay, next let's find our angles. Doesn't really matter which one we start with here. Let's go with x. Okay, so to find x, to find your missing angles, as long as you have two sides, we can use our inverse trig functions. So an inverse sine, inverse cosine, inverse tangent. We can use those inverses to find our angles pretty quickly. Now, since I already have, or I was already given 10 and 6, okay, I'm going to use these two sides to find my angles. I did find z. I know the hypotenuse is about 11.66, but that is rounded. So anytime I'm using rounded values to find other values, I'm going to be off by just a little bit. Okay, so if I want to be as exact as I can, using given values in these inverse trig functions, using my given values are going to give me a more accurate result. Okay, so I can use z if I wanted to, it's just not going to be as accurate as if I use given information. So I'm going to use these. Now if I go to my labeling here, so if I want to find x, I know the leg opposite of x is 6, so put an O here. My leg adjacent to x is 10. Again, this is the hypotenuse. I'm not going to use that one here. I'm going to use opposite and adjacent. So opposite and adjacent is going to be a tangent. Okay, so I'm going to use an inverse tangent function to figure out x. So tangent of x is opposite over adjacent. That would be 6 over 10. And to solve for that x, what we're going to do is we're going to take the tangent inverse of both sides. Okay, so a tangent inverse of a tangent function, those are, again, inverses of each other, so those are gone. And if I take the tangent inverse of 6 over 10, so second tangent gets me the tangent inverse of 6 over 10. And that looks like we're at about 31 degrees. Okay, 31 degrees for the measure of x. I'm going to write that in right there. So 31 degrees. Now I could do another tangent inverse. If I did the tangent inverse for angle y, all that would change would be my fraction would flip. Okay, it would be a reciprocal, so it would be 10 over 6 instead of 6 over 10. But again, since a triangle is 180 degrees, and because that one was really, really close to 31, I can just take 90 and 31, subtract that from 180, and I can get angle y, which would be 59 degrees. So that's probably the quickest way to go about that one. Okay, so this right triangle is solved. I've got all three angles, 31, 59, and the 90. Got all three sides, two of which were given. Pythagorean theorem to get the third, which was 11.66. All right, let's do one more. Okay, so my right triangle this time. Information given is going to be a side length of 3. We're going to go with the 70-degree angle up top. And then we're going to be missing this angle, the hypotenuse, and the longer leg at the bottom. That's a z. Go Okay. So let's start with angles. It's the quickest way to go if you already know 2 of the 3 angles once again. So if I've got a 70-degree angle, a 90-degree angle, you're already at 160 degrees. That means to make a triangle 180 degrees, that X angle is going to have to be 20. So 20 degrees for angle X. Okay, to go about finding my 2 other side lengths, this is where we're going to utilize sine, cosine, and tangent. Now I've got 2 acute angles here that I know. I've got 70 and 20. It doesn't really matter which one I pick. I was already given the 70, but since that's a whole number, I haven't rounded anything. I can really use the 20-degree angle as well if I wanted to. I'm not going to do that. I'm going to use the 70. So if I use the 70, again, if I label my sides, here's the 70-degree angle. Opposite of that is Z. Adjacent leg is going to be the 3, and then the hypotenuse is Y. Okay, so let's start with Y. Let's start with the hypotenuse. So I have the adjacent leg. I want the hypotenuse. So adjacent over hypotenuse, you can see that right here. Adjacent and hypotenuse is going to be cosine. So setting up a function for cosine, we're going to say cosine of 70 degrees. Cosine is equal to the adjacent leg, 3, over the hypotenuse, which is missing, that's y. So cosine 70 equals 3 over y. Put this over 1, take my cross product. I've got 3 times 1 is 3. Y times cosine 70 is y times cosine 70. And then to solve for y, I'm going to divide both sides by cosine of 70. Cosine 70. So that's 1. I've got y equals 3 divided by cosine 70. 3 over cosine 70. So that's what I can type into my calculator. So we can go 3 divided by cosine 70. Okay, 3 divided by cosine 70 is, we'll stick with the hundredths place here, we'll say 8.77. So we've got y equals 8.77. Okay, check for reasonableness here. The shorter leg is 3, 8.77, about 3 times the length. Again, my triangle's not drawn to any type of scale, but just to kind of ballpark it, eyeball it, that makes sense. 8.77 looks good. Okay, last thing, z. Okay, just like before, I could use Pythagorean Theorem. In this case, I could go a squared plus b squared equals c squared, but because I've rounded that 8.77, I'm going to kind of avoid that. I'm going to go back to my trig functions to solve for z. Okay, so back to the trig functions. Z is opposite of the 70-degree angle. 3 is adjacent, so opposite and adjacent. I can go over to tangent. So we're going to use the tangent function. Say the tangent of 70 degrees, which is the opposite leg, that's z, over the adjacent leg, which is 3. So I've got tan 70 equals z over 3. Take my cross product, I'm going to get z equals 3 times tangent 70. And I can go right to my calculator. 3 times tan 70. And 3 times tangent 70, again sticking with the hundredths place, we're going to say that's about 8.24. Check my pictures. 8.24 is a little less than the hypotenuse, 8.77. So again, hypotenuse always has to be longest. So I know I'm good on that one. Okay, and that's it there. We've got all 3 angles, 70, 20, and 90. All 3 sides, 3 which was given, z 8.24, and y 8.77. All right, so there you have it. That's how you go about solving a right triangle. Give this video a thumbs up if it was helpful for you, and feel free to subscribe to the channel to see more videos just like this one. As always, thank you for watching, and we will see you next time.